Hello my friends and welcome back to the You Can Do TV channel. The production process of AKSTMT steel bars begins with heating high-grade billets in a reheating furnace. This step brings the billets to the desired temperature for further processing. Once heated, high-pressure water jets are used to remove the oxidized layer from the surface through a descaling process. This ensures the billets are clean and free from impurities while maintaining a consistent temperature, which is essential for producing quality steel bars. Following descaling, the billets proceed to the rolling mill, which is divided into three sections. The first part, known as the roughing mill, shapes the billets into the desired form. AKS uses a combination of horizontal and vertical stands, which allows precise shaping without the need to rotate the billets. This method preserves the internal structure and enhances the strength of the steel bars. After rolling, the steel bars undergo thermomechanical treatment, TMT. This involves rapid cooling of the outer surface while keeping the core hot. This temperature difference forms a tough outer layer and a ductile inner core, resulting in TMT steel bars. The bars are then cooled on a 12-meter-long cooling bed, the largest in Bangladesh, before being cut and bundled. China's hot wound spring production industry is a key player in supporting heavy-duty applications across railway, automotive, mining, and agricultural sectors. These springs, made from large-diameter steel bars, typically ranging from 15 mm to 65 mm in diameter, are designed to withstand extreme mechanical stress and provide stability in demanding environments. The production process of hot wound springs involves several key stages: material selection and preparation. High-quality alloy steel bars, such as 60C2MNA or 50C-RVA, are chosen for their strength and durability. The bars are cut to specific lengths depending on the spring's design specifications. Heating. The steel bars are heated to temperatures between 850 degrees Celsius and 1050 degrees Celsius using induction or gas furnaces. This high-temperature process makes the material malleable for coiling. Hot coiling. Once heated, the steel is coiled around a mandrel or coiling machine to form the desired spring shape. Hot coiling ensures the spring retains structural integrity and uniformity despite its large diameter. Quenching and tempering. After coiling, the spring is rapidly cooled, quenched, in oil or water to increase hardness. It is then reheated to a lower temperature, tempering, to relieve internal stresses and improve toughness. Shot peening. This process involves blasting the spring's surface with small steel shots to enhance fatigue resistance and extend its lifespan. Load testing and quality control. Each spring undergoes rigorous testing to verify mechanical properties, including load capacity, hardness, and dimensional accuracy, ensuring compliance with international standards like ISO 9001, ISO 14000, and IRIS. China's hot wound spring industry benefits from the country's massive steel production capacity, approximately 226 million tons of steel bars in 2023, ensuring a consistent raw material supply. Increasing demand from railway and mining sectors drives technological advancements and production efficiency. With a focus on quality control and adherence to global standards, Chinese manufacturers continue to expand their presence in international markets, meeting the needs of heavy-duty applications worldwide. Crafting a gun at Holland & Holland is an intricate journey, combining traditional craftsmanship with modern technology. This process involves several key stages: barrels, stocks, action, engraving, and finishing. Each step is executed by master craftsmen, ensuring the creation of some of the world's finest sporting shotguns and rifles. The process begins with the barrels, which are the foundation of any Holland & Holland gun. Each barrel starts as two solid lengths of steel, which are precisely drilled, turned, and reamed to achieve a perfect internal and external shape. The tubes are then joined with exceptional care, ensuring perfect alignment and creating a smooth, elegant line. This process requires hundreds of hours of skilled labor to ensure the barrels are perfectly round and concentric. The result is a structure that is not only aesthetically pleasing but also immensely strong and reliable. The next stage focuses on the action, the mechanical heart of the gun. Each action is a sophisticated assembly of moving parts, engineered to work in perfect harmony with the barrels. This process involves cutting, filing, and fitting every component to exacting standards. Precision is critical to ensure smooth operation and minimal wear, allowing the gun to function effortlessly for generations. The action's complexity is matched by its mechanical elegance, providing both functionality and durability. The creation of the stock is another crucial aspect of the process. Stocks are carved from the finest Circassian walnut, a wood known for both its strength and its striking appearance. The wood is dried for several years to prevent warping and ensure longevity. Each stock is individually crafted to fit the customer, offering a bespoke experience. The shaping and finishing process involves detailed handwork to create a smooth, ergonomic form that perfectly balances the gun. This stage is deeply personal, as the stock forms the primary point of connection between the gun and its owner. Engraving is where artistry truly comes to life. Holland & Holland employs skilled engravers who transform each gun into a unique work of art. The designs range from the iconic royal scroll pattern to intricate game scenes and precious metal inlays. Each engraver has their own distinctive style, allowing for a high degree of customization. This process requires exceptional patience and skill, as even the smallest details are executed with precision. The engraving not only enhances the gun's beauty but also signifies the craftsmanship invested in its creation. The final stage is finishing, where all the elements are meticulously assembled and refined. In the finishing shop, skilled craftsmen perform the delicate work of tuning and perfecting the gun's operation. This includes fine adjustments to the ejector timing and trigger pulls, as well as polishing the wood and lacquering the metalwork. The checkering process, which involves carving tiny grooves into the wood for grip, is performed by hand to ensure precision. Every detail is carefully inspected to meet Holland & Holland's rigorous standards. Once this stage is complete, the gun is ready to leave the workshop and begin its life in the field. Sheffield Forgemaster's forging process relies on powerful hydraulic presses to shape and refine large metal ingots. The current 4,500-ton and 10,000-ton presses apply immense pressure to manipulate ingots weighing up to 300 tons, enhancing their structural integrity and mechanical properties. The process involves heating the ingots to extremely high temperatures to make the metal malleable before applying controlled force to shape it into precise forms. The upcoming 13,000-ton press will further expand capacity, allowing the production of larger, high-integrity components essential for industries such as defense and nuclear power. This advanced machinery ensures precision and efficiency in large-scale forging. The Durostal press forging process utilizes two advanced hydraulic presses with a pressing force of up to 40 meganewtons. These presses are used when hammering force is insufficient to deform large materials. With the aid of rail and free-moving manipulators capable of handling up to 50 tons, forgings up to 35,000 kilograms in raw weight are produced. For components weighing up to 45 tons, two 4-column, underfloor presses are employed. An electronic control system ensures precision, optimizing material properties, structure, and deformation levels through combined stretching and upsetting methods. This section is about producing a custom motorcycle forkfoot made of 42 CRM04 on a Quasar MF400U 5-axis machining center. This alloy steel, known for its strength and toughness, requires advanced machining techniques to maintain tight tolerances and structural integrity. The MF400U utilizes its simultaneous 5-axis capabilities to perform complex machining operations in a single setup. The workpiece, a solid block of 42 CRM04, is securely fixed on the 320mm rotary table, which can accommodate parts up to 400mm by 300mm in size. The rotary table's low-friction design ensures smooth and precise movement, allowing for continuous multi-directional machining without repositioning the part. The machining process begins with roughing operations to remove the bulk of the material. Using high-speed 12,000 to 20,000 RPM spindles and 40 taper tooling, the machine performs aggressive cuts while maintaining stability. The tool magazine, with a 30-tool capacity, enables rapid tool changes, allowing for a seamless transition between roughing and finishing operations. During finishing, the 5-axis system precisely contours the complex geometries of the fork foot. The synchronized motion of the X, Y, and Z linear axes, combined with the A and C rotary axes, allows for intricate undercuts and tight radius features, ensuring a smooth, accurate surface finish. The symmetrical slide structure enhances stability and reduces vibration, critical when working with hardened materials like 42 CRMO4. This precise motion control minimizes dimensional deviation and enhances part consistency, ensuring that each fork foot meets the required specifications. The aerospace landing gear cutting process involves precision CNC machining using Mastercam software on the Haas VF1 and Centroid A565 axis machines. The process begins with roughing on the Haas VF1, where OptiRest toolpaths optimize material removal. A 2 inches fly cutter performs roughing with a 0.5 depth of cut and a 0.400 step over, ensuring efficient stock removal while maintaining accuracy. This initial roughing stage prepares the part for more detailed finishing. Once the first side is completed, the part is transferred to the Centroid A560 for 5-axis finishing operations. The A560's multi-axis capability allows for machining complex geometries and achieving the tight tolerances required for aerospace components. This combination of roughing and finishing ensures high precision and surface quality. The Gleason Titan grinding machines are advanced systems designed to improve the efficiency and precision of cylindrical gear manufacturing. These machines combine threaded wheel grinding for rapid material removal and profile grinding for superior surface finish and complex gear modifications, reducing finish grinding times by up to 50%. The process begins with the loading of a threaded grinding wheel, followed by the patented dressing concept, which does not require a setup. The swiveling dressing unit enables the dressing of both the right flank and the finishing grinding wheel, ensuring accuracy. During roughing, the machine uses a special rough grit size wheel for high material removal rates. The system is capable of handling gears up to 1,500 mm in diameter, module 14, and 84 teeth with a helix angle of 11 degrees. A high-speed automatic tool changer allows seamless switching between threaded wheel grinding and profile grinding within 1 minute, eliminating interference between the workpiece and grinding tools. The external setup table allows parallel preparation of workpieces, further reducing downtime. The universal dresser can dress both types of grinding wheels, minimizing tool changeover time. The Titan machines are controlled by Siemens 840 DCNC and Gleason Windows software, ensuring optimal production efficiency and ease of use. Kaplan turbines are widely used in low-head, high-flow water applications, such as hydroelectric power stations, where they convert water flow into mechanical energy. The design and manufacturing of Kaplan turbines require extensive experience and precision engineering. The process starts with dynamic flow simulations conducted in-house by highly trained engineers using state-of-the-art technology. These simulations allow for the optimization of the hydraulic characteristics of the turbine, ensuring that the turbine is tailored to meet specific site conditions. The results are carefully analyzed to create a 3D model of the turbine using advanced CAD, computer-aided design, systems. Once the design phase is completed, the manufacturing process is simulated and programmed using CAD, CAM systems to ensure that the production runs smoothly and efficiently. The precise adjustment of the turbine blades is particularly critical, as their geometry and positioning directly affect the turbine's performance. Engineers also use finite element analysis, FE, to evaluate the structural integrity of key components, ensuring they can withstand the high mechanical stresses encountered during operation. The Kaplan runner is typically constructed from high-quality, corrosion-resistant materials such as stainless steel or ductile cast iron, chosen for their durability and ability to withstand harsh operating conditions. Before manufacturing begins, the materials are carefully inspected for any flaws or defects that could compromise the turbine's performance. The manufacturing process for the Kaplan runner blades is labor-intensive and precise. Each blade undergoes a meticulous milling process that can take up to 60 hours, depending on the size and material of the turbine. The blade surfaces are polished by hand after milling to achieve a smooth finish, and each blade is inspected according to ISO standards to ensure it meets stringent quality requirements. Surface crack and pore testing is performed using two-color dye penetration techniques as per DIN ISO regulations. Once the individual components of the Kaplan runner are manufactured, they are assembled with the highest degree of precision. 3D measurements are used to verify that the turbine blades and other parts are perfectly aligned. This ensures the turbine will operate with maximum efficiency and reliability once installed. Before delivery, all Kaplan turbines are tested in-house to verify that they meet the design specifications and to eliminate any potential sources of error. These tests include performance checks and tolerance assessments to ensure that the turbine functions as intended in real-world conditions. In an era where sustainable energy is a critical global priority, Kaplan turbines offer an ecological solution by harnessing the power of water to generate electricity without damaging ecosystems. These turbines, equipped with adjustable blades and wicket gates, are designed to efficiently adapt to fluctuations in water levels and flow rates. The Kaplan runner, as a core component, is crucial for optimizing the turbine's performance. The manufacturing of submersible motors and hydrodynamic screw turbines begins with precision engineering and optimization. Experienced engineers design pump models tailored to specific applications, ensuring optimal performance and efficiency. The process starts with material selection, followed by foundry work to cast the components. These parts undergo rigorous heat treatment to enhance their strength and wear resistance. Key to the manufacturing is the CNC milling of impellers, which requires exacting precision to ensure efficient fluid movement. Hydrodynamic screws and multi-stage submersible pumps are designed to handle high pressures and provide outstanding operational reliability. Each stage of the production is tightly controlled with strict quality management to guarantee product durability and performance under the most demanding conditions. After assembly, extensive testing is conducted to meet industry standards and certifications. Vertical line shaft pumps are versatile solutions for a range of industrial needs, including irrigation, drainage, and seawater intake for desalination plants. These pumps can handle flow rates up to 20 cubic meters per second and heads of up to 80 meters. Depending on service conditions, materials range from cast iron to high-performance steel grades like duplex and superduplex. Designed for axial, semi-axial, or radial flow, they feature wear-resistant bearings for extended service life. The manufacturing starts with the casting of the main parts, including the pump housing and shaft. The next critical phase is machining. The pump shafts are milled and finished to exact dimensions, while the impellers, crucial for regulating flow, are CNC machined to achieve high efficiency. The bearings, which ensure smooth operation, are made from wear-resistant materials to maximize pump longevity. Depending on the design, axial, semi-axial, or radial, the manufacturing process adapts to the specific hydraulic requirements. Once all parts are produced, the assembly process begins. The components are precisely aligned and installed to ensure optimal performance. Quality control is essential, with rigorous testing of flow rates, head capabilities, and operational stability under various conditions. The SR steel plate mill with a capacity of 1.5 MTPA is India's widest plate mill, producing 5 meters wide plates. The steel plate production process here begins with slabs from the steel plant being reheated in a digital reheating furnace. These slabs are then passed through a reversing rolling mill, which imparts fine grain properties to the plates. The plates are further processed using thermomechanical controlled rolling with accelerated direct cooling and quenching to enhance abrasion resistance, formability, and toughness. After rolling, the plates are cut to customer specifications using universal torch cutting machinery and undergo quality checks through manual ultrasonic testing. Heat treatment facilities provide normalized, quenched, and tempered plates for specialized applications. The Fachin HAV4 is a powerful, heavy-duty 3-roll plate roller with variable geometry, designed for forming large cylindrical and conical shapes used in offshore wind tower foundations such as monopiles, transition pieces, jackets, and tripods. It operates by positioning the steel plate between 3 adjustable rollers. The bottom rollers move laterally to create the desired bending radius, while the top roller applies downward pressure to shape the material accurately. This variable geometry system allows for precise pre-bending and rolling of thick plates, reducing flat ends and ensuring high roundness tolerances. With a maximum plate width of 4,200 mm, rolling thickness of 240 mm, and pre-bending thickness of 200 mm, the machine handles large-scale fabrication with ease. The production process of the GWF Gigant Press involves the precise assembly and welding of oversized components. Due to the massive material thickness, all weld seams undergo a 100% ultrasonic inspection by independent experts to ensure quality. After welding, individual parts are machined for greater precision. Large components are transported using specialized lifting equipment. Critical sections, such as the side columns and press table, are finely milled and drilled for accurate assembly. Every stage, from manufacturing to transport and installation, follows strict quality controls to ensure flawless operation. PT Indonesia Asahan Aluminium, Inalum, Persero operates an advanced aluminum smelting plant in Kuala Tanjung, Batubara, North Sumatra. The plant, with an installed capacity of 225,000 tons of aluminum per year, utilizes state-of-the-art technology to produce high-quality aluminum billets. The production process begins with the transfer of molten aluminum from the reduction pot to the holding furnace. This molten aluminum undergoes treatment to remove impurities and gases, ensuring superior product quality. After the purification stage, the chemical composition of the aluminum is analyzed to determine the necessary addition of master alloys. Homogenization of the molten aluminum is achieved through electromagnetic stirring, ensuring uniform chemical composition. Once the composition meets specifications, the molten aluminum proceeds to the casting stage. PT Inalum employs a vertical direct chill (VDC) casting system using gas ion technology, which produces billets with smooth surfaces and refined microstructures, maintaining a cell zone of approximately 100 micrometers. Before casting, the molten aluminum undergoes degassing with argon gas to eliminate hydrogen and passes through filters to remove residual impurities. The cast billets are subjected to ultrasonic inspections to detect surface and internal defects. Following inspection, billets undergo a homogenization process to enhance metallurgical properties and mechanical strength. The final billets are cut to standard or customer-specified lengths, bundled, and stored for shipment. Quality control is maintained through accredited laboratories equipped with advanced instruments to ensure compliance with international standards. The metal saw billet cutting machine operates with advanced technology to deliver high-speed and precise cutting for both ferrous and non-ferrous materials. The process begins by feeding the metal billet into the machine, where automated controls position it accurately. The saw utilizes precision blades and high-torque motors to perform clean, consistent cuts, even on the thickest materials. Rockwell automation systems ensure smooth operation and allow remote monitoring through an Ethernet connection for real-time production tracking. Customizable features help reduce errors and increase output efficiency. The machine is designed for easy maintenance and operation, ensuring minimal downtime while providing rapid, accurate cuts for high-volume metal service centers and extruders. The automatic new energy motor stator manufacturing process is a highly automated and advanced system designed for the production of electric vehicle (EV) motor stators. Artificial alignment and first expansion. The process begins with manually aligning and positioning the stator core. The first expansion step involves slightly expanding the stator slots to facilitate the insertion of insulation materials and coils. Winding and secondary embedding. The stator coils are wound and inserted into the stator core. This step ensures the even distribution of copper windings. The secondary embedding involves securely positioning the coils within the stator slots for stability and performance. Manual wiring. Manual wiring involves sorting and arranging the wire ends from the third phase. This step also includes inserting copper tubes and preparing the stator for the subsequent welding process. Tooling installation. Specialized tooling is installed to hold the stator in place during subsequent automated and manual processes. This ensures precision and consistency throughout the production line. Star welding. The star point connection is formed by welding copper tubes to the coil ends. This step is essential for the electrical connection between the stator windings and the external circuit. Fine shaping. Fine shaping or middle forming involves reshaping the stator coil ends to meet precise specifications. This step ensures uniformity and optimal performance of the motor stator. Double-sided binding wire. Both sides of the stator undergo automatic lacing with nylon or other binding materials. This secures the coil windings and prevents movement during motor operation. Stator slot expansion. The slot end paper is expanded automatically to provide insulation protection and enhance mechanical stability. This step prepares the stator for the final assembly stages. Manual inspection of upender. The final step involves manually inspecting the stator for quality assurance. This includes testing for voltage, phase sequence, and resistance. The stator is then delivered via a double-speed flow chain system for further processing or shipment. The production line is equipped with a manufacturing execution system to enable process traceability. It achieves a cycle time of less than or equal to 170 seconds per piece and allows for full tooling changes within 2 hours. The system ensures a 100% reliability rate for testing and an online inspection rate for key parameters, making it an efficient and precise solution for new energy motor stator manufacturing. We're in Giant's advanced composite manufacturing facility in Takia, Taiwan. The production process here begins in the loom room, where raw carbon threads are woven into composite sheets. This stage is critical, as these sheets form the foundation of the bicycle frame. In the layup room, over 500 individual composite swatches are carefully cut, arranged, and layered to form the initial structure of the frame, known as the soft frame. Each layer is strategically placed to enhance strength and performance. This soft frame is then transferred to the molding stage, where it is positioned inside a steel mold. The mold undergoes high temperature and high pressure processing, solidifying the frame's shape and ensuring structural integrity. Once molded, the frame moves to the finishing and painting rooms. Here, it is hand-sanded to a smooth finish, meticulously painted, and adorned with decals. A clear coat is applied for protection and a polished appearance. The process concludes with a rigorous final inspection. Each frame undergoes 14 individual quality control checks across 9 hours of labor and 32 pairs of skilled hands. This process results in the creation of a premium TCR Advanced SL bicycle. The 20-ton copper to aluminium friction welding machine joins bimetallic parts by generating heat through rotational friction. It features a pre-machining unit that mills the copper palm and aluminium rod ends, removing oxide layers. The cleaned surfaces are then pressed together under high force, creating a strong, defect-free metallurgical bond. Elco Block 36M fully automatic multi-layer concrete block making machine operates by compressing concrete in molds designed for various products, including interlocking paving stones, curbstones, and blocks. Each production cycle is completed in 24 seconds. The machine features a high-performance multi-circuit hydraulic system with 3 hydraulic pumps and proportional valves to control speed based on the product type. It uses an amplitude and frequency-controlled vibration system to ensure optimal compression and quality. The machine includes automated height adjustment for feed drawers and hydraulic discharge-controlled bins with level indicators for precise material handling. Fast mold-changing capabilities allow quick product transitions. The Langenpreselten pump storage plant, located in the Unterfranken region of Bavaria, Germany, plays a critical role in Deutsche Bahn's railway system by supplying peak load power. Recently, the world's most powerful single-phase hydropower motor generators at Langenpreselten were scheduled for refurbishment. One of the most impressive components of the refurbishment is the rotor, which is subjected to centrifugal forces that reach an astonishing 27,000 tons per pole. This level of force is comparable to the weight of 70 fully loaded Boeing 747 jumbo jets, emphasizing the immense power involved. The rotor and its poles must withstand not only mechanical stress but also significant thermal expansion and currents as high as 34,000 A. Manufacturing the forged shafts required for this project was a significant challenge. Only a few forges in the world are capable of producing the necessary flawless quality for these components, which weigh around 170 tons. Comprehensive testing was performed to ensure the strength and stability of the damping system, which includes poles weighing 34 tons each. The assembly of the generators required extreme precision. The plant's crane, with a maximum load capacity of 110 tons, necessitated that the stator housing be assembled in parts inside the generator annulus space. Similarly, the rotor was carefully assembled within the stator to complete the installation. With the project nearing completion, the Langenpreselten pump storage plant is set to resume operations, continuing its crucial role in supplying peak load power for Germany's railway system. With an output of 2 times 94 MVA, the plant provides enough electricity to power 50 intercity trains traveling at speeds of 200 kilometers per hour. This essential function is made possible through the use of powerful single-phase hydropower motor generators, which are tailored specifically to operate within the railway's 16.7 Hz traction power network. Decanter Centrifuge Service focuses on providing comprehensive maintenance and repair solutions to ensure peak performance of centrifuge components, such as scroll conveyors. The service is supported by a state-of-the-art balancing machine capable of 4,000 revolutions per minute, with a 6-ton capacity, a 6-meter working length, and a 2-meter diameter. This advanced balancing bunker allows for the precise balancing of decanter parts at their typical operating speeds, ensuring that once reassembled, the parts operate smoothly with minimal on-site downtime and no unexpected issues during restart. In addition to balancing services, the Decanter service offers a wide range of specialized solutions, including gearbox reconditioning, the welding of tungsten carbide tiles for enhanced wear protection, and an eco-friendly dry ice blasting process for cleaning. These services are designed to maximize equipment performance and lifespan. The Sobrigino hydroelectric power plant, controlled by San Francisco Hydroelectric, is undergoing a significant modernization and digitization project. Located on the São Francisco River in Bahia, Brazil, Sobrigino was inaugurated in 1979 and is one of the largest plants in the region, with an installed capacity of 1,050 megawatts. The project focuses on refurbishing 6 generating units and vertical Kaplan turbines, which have been in operation for over 41 years. The dam spans 59.4 square kilometers, with a reservoir that stores up to 34.1 billion cubic meters of water. This modernization aims to improve efficiency and ensure long-term sustainability in this crucial water source for northeastern Brazil. The production of a Francis runner plays a vital role in the functioning of Francis turbines, which are widely used in hydropower plants for generating sustainable energy. These turbines operate efficiently in medium water head ranges, making them ideal for power plants where water flow is constant. The Francis runner is the heart of the turbine, responsible for converting the energy of flowing water into mechanical energy. The design process of the Francis runner starts with advanced 3D modeling, involving cutting-edge technologies and computational simulations. Engineers collaborate with recognized institutions and use dynamic flow testing to ensure that the turbine's geometry is optimized for efficiency. This stage is critical for guaranteeing that the runner will perform effectively under various operating conditions, ensuring high power output with minimal losses. Once the design is complete, the machining process is programmed using a CAD/CAM system. The system simulates the milling operation to check for collisions and interference between the CNC machine and the workpiece. The Francis runner is typically made from forged high-alloy stainless steel, chosen for its high tensile strength and wear resistance, which are essential for the harsh environments inside the turbine. Milling the runner is a complex task, requiring up to 400 hours of machining on a 7-axis CNC machine. The machine is capable of cutting intricate shapes without repositioning the material, ensuring precision. For multi-section runners, the parts undergo heat treatment to enhance durability. After milling, the runner undergoes hand polishing to ensure a smooth surface, which is essential for minimizing friction and turbulence in the water flow. Once polished, the runners are dynamically balanced according to ISO 1940 standards, ensuring stable and efficient turbine operation. Following production, the runners are subject to meticulous quality checks. 3D contour measurements are taken to verify that the runner matches the design specifications. These checks ensure that the runner will fit perfectly within the turbine and achieve optimal efficiency. Before shipment, the runner undergoes a pressure test to ensure structural integrity. The runner's casing is filled with water, and pressure is applied for an extended period, monitoring for any signs of leakage or failure. This test is conducted according to European pressure vessel regulations, ensuring safety and reliability. Once the testing is complete, the runner is prepared for shipping, ready for assembly at the customer's hydropower plant. A Francis turbine is a type of hydro turbine commonly used for medium head applications in hydropower plants. It operates by converting the potential energy of water into mechanical energy. Water enters the turbine through spiral casing and is guided by adjustable guide vanes that control the flow rate. The water flows through the runner blades, which are curved to efficiently capture the energy from the water's velocity and pressure. As the water passes through, it causes the runner to spin, driving a connected shaft that generates electricity via a generator. The water exits through a draft tube, maintaining a pressure difference that ensures a steady flow. The design is efficient for a wide range of heads and flow conditions, making it a versatile choice for hydropower stations. Hydropower is one of the most efficient forms of renewable energy production. Upgrading and optimizing hydropower plants can significantly increase profitability. In fact, about 50% of hydropower plants are over 40 years old, and there is a growing demand for new hydropower installations and equipment. This facility is a leader in the market, specializes in the service and rehabilitation of hydropower facilities. With more than 170 years of experience in turbine design, the facility has installed over 30,000 units worldwide, amounting to more than 300,000 megawatts of capacity. They offer a full range of solutions, up to 800 megawatts, aimed at rehabilitating, modernizing, and increasing the capacity of hydropower plants. Rehabilitation and modernization provide many advantages. First, they improve energy production by optimizing the use of available water resources, leading to increased revenue. These processes also help reduce maintenance and service costs, while ensuring compliance with environmental regulations. Additionally, modernization increases reliability, making plant operation more dynamic and suitable for grid regulation. However, modernization is complex. Leveraging its extensive experience, the facility has developed a structured diagnostic, analysis, and therapy process to ensure maximum benefits for hydropower plant owners during renovation projects. Their interdisciplinary approach to research and development focuses on optimizing hydraulic, mechanical, and electrical performance. This involves advanced research in fields like coating technology, material science, fluid dynamics, electrical design, and structural mechanics. The facility collaborates with universities and partners worldwide to apply this research in practical applications. An overhaul is a crucial maintenance process for industrial equipment, particularly for large machines like hydro generators. In the context of hydroelectric power, overhauls ensure that the generators, which convert mechanical energy from water turbines into electricity, continue to operate efficiently and safely. Without regular overhauls, the performance of these machines can degrade over time, leading to decreased efficiency, costly repairs, or even catastrophic failures. For example, a typical hydro generator operates continuously under heavy loads, generating thousands of megawatt hours of electricity annually. Over time, components such as bearings, seals, and electrical insulation systems experience wear and tear. A thorough overhaul, conducted every 10 to 12 years, involves dismantling the entire unit to inspect and repair or replace key components. During this process, technicians assess the condition of the rotor and stator, two of the most critical parts, each weighing several tons. Replacing or refurbishing bearings, which often cost between $10,000 and $50,000 depending on size and design, is a common task. In addition, upgrades to control systems, which can range from $500,000 to $1 million, are often implemented during the overhaul to improve efficiency and incorporate modern technologies. An overhaul can take several weeks, requiring a team of 10 to 15 skilled workers and typically costing between $2 million and $5 million. While this may seem expensive, the financial and operational risks of not performing an overhaul far outweigh the costs. By ensuring the hydro generator operates at peak efficiency, overhauls extend the lifespan of the equipment, reduce the risk of unplanned outages, and maintain the reliability of the power grid. The Sir Adam Beck 1 Powerhouse, located on the Niagara River in Ontario, Canada, recently underwent significant upgrades. The project involved the replacement of turbine and generator units G1 and G2, which had been decommissioned since 2009. These new installations feature modern components with a standard frequency of 60 Hz, along with a headgate refurbishment and electrical upgrades to enhance the plant's overall efficiency. During the project, it was determined that the 100-year-old scroll case could not be repaired and needed to be replaced. Despite the technical challenges and the difficulties posed by the COVID-19 pandemic, the replacement work was completed successfully within a year. At the core of the Chievo Dam's Hydromatrix plant lies a steel-fabricated module, situated at the downstream end of the ship lock. The module houses 5 Straflow matrix turbine generator units, which are crucial to the plant's energy generation process. At the upstream end of the module, an intake trash rack ensures the smooth flow of water, while the turbine units convert the water's kinetic energy into electricity. Below the turbines, 5 draft tubes channel the water through the system. Above the draft tubes, a submerged equipment gallery contains the hydraulic power unit, which operates the gates controlling water flow. The module is designed to be raised and lowered by a gantry hoist system, enabling the lock chamber to be evacuated before flood releases. One of the innovative aspects of this project is the Straflow matrix turbines used in the Chievo Dam plant. These axial straight flow turbines are smaller and lighter than conventional Hydromatrix turbines, making them ideal for locations with space constraints, such as the narrow confines of the Chievo Dam. The turbines connect the upstream and downstream reservoirs via straight tubes, with the generator mounted directly on the turbine's periphery. This compact design ensures efficient power generation without requiring additional space. Each turbine unit is composed of several key components, including a distributor cone, a generator rotor, and fixed propeller blades made from corrosion-resistant steel. These components are assembled with precision, and the final step involves machining the rotor's outer rim to prepare it for the installation of permanent magnets. Andritz Hydro employs permanent magnet technology for the synchronous generators, which easily connect to the local grid without needing power factor compensation. The manufacturing and assembly process for the turbine generator units takes place at Andritz Hydro's workshop in Wise, Austria. Once assembled, the units are transported to the Chievo Dam, where the lock walls and sill area are adapted for their future role in hydropower generation. A temporary coffer dam is erected to separate the lock from the river during construction, while the lock sill is reinforced with stainless steel plates. Meanwhile, a fish ladder is constructed along the embankment to facilitate fish migration and mitigate the environmental impact of the dam. The final stages of the plant's construction involve installing and securing the turbine generator units onto the steel module structure. A new gantry hoist system, equipped with an auxiliary hoist, ensures that the units can be easily removed for maintenance. Power and control cables are routed through the module to the landside generator switchgear. A trash rack cleaning machine is installed to keep debris from clogging the intake, maintaining optimal performance of the Hydromatrix plant. The Chievo Dam Hydromatrix plant was successfully commissioned many years ago, generating enough electricity to meet the needs of approximately 10,000 households. This innovative project serves as a model for how modern hydropower technology can be integrated into existing infrastructure, such as locks and dams, while preserving their flood control capabilities and minimizing the need for extensive civil works. Moreover, the project had no adverse effects on Verona's beautiful historical and recreational areas. The Chievo Dam Hydromatrix plant stands as a shining example of sustainable energy development. By harnessing the power of water at a previously unused shiplock, the plant fulfills the vision of its owners, Consorzio Canali Camazzoni, while contributing to Italy's renewable energy goals. A headbox is a critical component in paper, board, and tissue machines, responsible for distributing the pulp slurry evenly onto the forming wire to create uniform sheets. Over time, the performance of the headbox can degrade due to corrosion, damage to the slice and apron lips, wear on adjustable parts, and defects in heating channels. This deterioration can negatively affect sheet quality, operational safety, and efficiency. To avoid costly downtime and ensure continued productivity, it is essential to maintain and overhaul the headbox regularly. This service helps extend the equipment's lifespan and improve sheet quality while protecting the initial capital investment. The overhaul process includes engineering, disassembly, reassembly, and precise adjustments to the headbox. All movable parts and drives, including the apron or slice lips, are inspected and repaired. Additionally, new heating units can be installed, and damaged diffuser tubes can be manufactured and exchanged.